My name is Andrew Darrow, Eric Schmar, and our research paper that we had to read was on a program called discovRE. Like it says, efficient cross-architecture identification of bugs in binary code. So brief overview of what we're going to cover. A little introduction into what it is, the high-level concept and compatibility of the program, and then we get into some of the structure of the program containing numeric filtering, structural similarity, the bug searches that they did, the results, their limitations, and then the related works and our conclusion. So what is discovRE? It was a tool that was developed and used to identify vulnerabilities at the binary level. They chose the binary level because most projects are closed source, and so you might not have access to the actual source code. And then it also helped with being able to go across platforms, as we'll talk about later on. Why was this important? Obviously, as we learned in this class, software security is a must, and especially for big companies that release lots of software, public trust is a big thing. So if you lose the public trust, then you are going to be failing financially. And then this program uses a series of filtering, which we'll also discover or talk about. So this is the overall concept. We start with the code base. We go through some feature extractions, get numeric and structural features. We put it into a similarity computation, and then we pop out some matches that could be possible vulnerable programs. So the code base, the people that did this paper, they used 4 widely used compilers listed there: GCC, CL, which is Clang, ICC, and then Visual C. They used 3 different CPU architectures, the basic Intel 86 and 64, then an Android ARM version 7. They used both Windows and Linux operating systems, and then they built their code base with the 7 well-known open source projects that are listed here. All these projects compiled together, they ended up using over 1,700 unique compiler options. So they went through and just used different compile option over different compile option to recompile it basically over 1,700 times. They only excluded function inlining as a compiler option because it would have caused code overlaps. And then they actually took those 1,700 different compilation options and they compared them against each other and found out with using SSDeep with a minimum similarity score of 95, they got that number down to about 600 compiling options so that they didn't have to run through all 1,700 every single time. Then they used a program called IDA Pro as a disassembler, as it already supported the vast amount of the CPU architectures that they were going to use. So they didn't have to come up with something new or use multiple programs. And then when you get into the feature extraction, how they did their extraction, they used both numeric and structural. The numeric features, basically they counted the number of the different structural features, like number of instructions, the size of local variables, the number of parameters, the functionality classes. And as you can see from the diagram there, they ran all these through and they computed an average correlation and a standard deviation. And they chose the ones that had the highest average correlation and the lowest standard deviation, so that everything was similar throughout the process, and they had a robust amount of features.
Okay, so what we have to remember here is that they're comparing code at a binary level, which means they have to have some sort of representation of the vulnerable function that they want to check against and the functions that they're checking. So if you remember from other presentations, they talked about control flow graphs, where it's based on things like conditionals, function calls, basically any way that the program can run through. And it represents the logic of a function. So you want to remember that later because we talk a lot about it for some of the other things that we go over. So the first thing that I'm going to talk about is the numeric filter, which Andrew brought up. They use an algorithm called the k nearest neighbors. Basically, it's a statistical algorithm that takes a multi-dimensional set of variables, dimensions here being the things that he talked about, so like number of parameters, stuff like that, and classifies them into groups. This is just an image taken off Wikipedia to give you an idea. So the goal is to find what points are related. So if we are given a point like this one, we can ask it which other points are related to it, and we can have a list of potential points. So here we're going to be worried about which CFGs are related between the vulnerable functions and the one that we're looking, or the ones that we're checking. So they worried about optimization because obviously if you have a large code base, you could potentially have a lot of things that you need to check. And so one of the things they did was they normalized the data, which meant that the variables could have wide ranges. So for instance, size of variables could be anywhere between 8 bytes to 64 or whatever. It's a large range and it's harder to classify on that. So they normalized it to an interval between 0 to 1. And then they evaluated it using OpenCV's fast library for approximate nearest neighbors. And there's 3 options you can do. There's the linear index, the hierarchical k-means, and KD trees. They have big names, but they're pretty easy to understand. The linear index runs, it's probably the slowest running time, and it basically just it stores the nearest neighbors in a priority queue, and then you just query the queue. So if you want the next nearest neighbor, you just pop that off the top. And then hierarchical k-means, which had a log-n running time, recursively split the data into small clusters with the goal of maximizing the distance between clusters. The graph that I had earlier might not be very good, but so it'd take a cluster of here with a larger distance between these, and it'd separate them into those, and they would potentially be the ones that you want to check. And KD trees is the last one. This ran in log-n time. They're multi-dimensional binary search trees, and what I mean by that is they have a dimension for each variable that was included in the k nearest neighbors algorithm. And so you create one tree based on one variable, another tree based on another variable, and then you can have you can query them in parallel because you're looking for ones with you only care about the certain variables. But before we decide which one of these filters from FLAN to use, they were also pretty concerned with reducing the dimensions, so reducing the number of variables we care about. So like I mentioned before, if you have a lot of different things that you're using for the KNN algorithm, it could result in a large running time because say you have, like a 15-dimensional KD tree, you would have, 15 different trees you have to run through. And so they reduced the number of variables to 5, which I think they really, they first tested it on the KD trees, and that's what they ended up going with. And you can see this graph is pretty important because this shows that the setup time for KD trees, it's yellow, it's this line, is not the best setup time, but the query time for KD trees, which is again in yellow, is absolutely the fastest. So with a little bit of processing in the beginning, you can have extremely fast query times, which means that at least for the user, you could set it up and then you can query it almost instantaneously. So next, we're on structural similarity. This is where the CFGs come in. So we're comparing the CFG of a candidate function that we know to be vulnerable with functions in a code base that we don't know whether or not they're vulnerable. So one option is to compare the CFG itself, which people have already been doing, but we want to do it better. So these researchers developed the idea of basic blocks, which are just machine codes, like machine code. I don't want to call them functions. They're blocks with one entry and one exit point. So like one function call, if it's an if statement, you enter into it, etc. And so they really were concerned with the connections between basic blocks. If one block called another one, then it was important. So the way that they compared these basic blocks was just doing a simple distance. I say distance, it was kind of complicated, to be honest. And so they introduced a concept of a node, which is made up of basic blocks. And you want to keep track of each node's properties. So like, there's labels that like the compiler uses into the bytecode, and that's what like disassemblers can use as well. They also keep track of strings and constants and other features, such as the number of logic instructions. So like a block might be similar if it had exactly 3 logic instructions, and the number of function calls, the same reason. And so they calculated well, actually before that, they ended up running something called a genetic algorithm on these properties, and they found that over here, the alpha, you want a higher alpha for it's more important. So the number of function calls and the number of logic instructions turned out to be a better determining factor of basic blocks, like it's a property you should care about. And so what they did is they just calculated the distance between nodes. And so a node that's further away means it's less similar. They have, a complicated algorithm or it's really just like a math thing, but it's, and so we're really just concerned with nodes that are closest. You can think back to that graph, you want nodes that are right by each other, indicate that they're more similar. And finally, we're calculating the similarity between the CFGs. So before we were looking at the actual bytecode, but you can also determine if 2 functions are similar by actually looking at the control flow graphs. The way that they did this was looking for the maximum common subgraph, and that's a fancy way of saying take your vulnerable function and a candidate function. You want to find a control flow graph that is contained in both and is also the largest control flow graph you can find. And this is complicated. It's an NP complete problem. But luckily, the reason why they use those numerical features was so that you can prune out all of the CFGs that make it not a candidate anymore. So it becomes much easier. And so our goal is to end up with 2 CFGs that have a lot of small distances between the basic blocks that they're made up with.
Okay, so once they got all that set up, they actually wanted to do this on a real-world case, and so they actually contacted the people who did a 2015 experiment, Puny et al. It was, let's see, cross-architecture bug search and binary executables. They created a program that did a similar thing, and they were looking for the heartbleed in OpenSSL, and so they actually got that group to send their binary files that they used to them so that they could use the exact same binaries that were used in the original project. And then they searched for the vulnerability in 3 different sources, self-compiled binaries, router firmware, and then a NOS device. And then they used a computer system that was very similar to the Puny paper, as you can see here. Listed the specs. They said it was actually a little bit slower than the computer that they used, but the big difference between the 2 searches was that this program actually searched all binaries, and they didn't actually extract anything from the OpenSSL libraries like the Puny paper did. And you can see the times. The big difference here is the rank. This discovRE ranked it as the #1 suspect for being a vulnerability, whereas the KNN, KD trees by themselves got it as ranked as 5.5. The query time for that was a little bit faster, but giving up the little bit of speed to get the actual #1 suspect was pretty good. And then comparing it to the Puny paper, their slowest or their fastest time was 18.7 minutes to find one, whereas this was down to 14 milliseconds. So this is a lot faster speed. You're not waiting, as you can see in the middle one there, 286 minutes. And then on this slide, they actually put all the building blocks in, which end up being, as you can see, the basic blocks. There's over 4 million. And they ran through with theirs, and they estimated that the times down here for the puny projects based off of the times that were given on the last slide, how fast it would take them to go through the whole 4 million, almost 5 million basic blocks. And you can see ours are still in the milliseconds, whereas theirs would be in quite a few minutes, up to days to complete.
And so finally, we're on to the limitations of the paper. First of all, it wasn't built to handle heavily obfuscated code. Luckily, there's open source projects that can deobfuscate most any code. And it only works on the function level, so not sub-functional level, which means that when you inline a function with that compiler option, you would lose the basic block generated from that function, and so it breaks this. Luckily, we can still just pinpoint bad functions or candidate functions, and even if we overestimate and give more, it's still good because they can check those by hand. And finally, low complexity functions aren't good either. They only considered functions with at least 5 building or basic blocks. If it was too small, it basically had a lot of collisions with other ones. And there's a lot of related work. Measuring code similarity, there's token-based approaches, abstract syntax tree-based approaches, ones that are scalable, strictly matching CFGs, which I mentioned above, opcode k-grams, think like DNA matching, where you take strings of opcodes and you try and match them together. And they use stuff like symbolic execution and a theorem prover, but code modification breaks it, and they're generally complicated and longer runtimes. There's also ones that are based on input-output behavior strictly. There's a search engine for binary code. There's a lot that were listed. And finally, the takeaway is we can mix these numeric and structural filters that I talked about to yield extremely fast search results. They found Heartbleed and Poodle way faster than the next prominent paper. They modeled all of this to be efficient across multiple architectures. We talked about all the compiler options. And that was a big point in this, was to make sure that it really didn't matter where you were using it, it was still able to find it. And I really got the impression that it was better than any single tool out there. Like, there was a lot of tools that did the same type of job, but this was just strictly better. Any questions? Sure.
I might be slightly confused. However, with the blocks we were talking about earlier, or the nodes, is there any way that one could call to another node and not get answered back?
So the question was, with the basic blocks, if a node calls to another node, could it not be called back? And absolutely. So in that case, it would probably be considered an exit. So there's an entry point into that node, and that would be the exit because it's no longer returning. And so the node that it calls to, that would be its entry point, and I don't know where it would exit, but there would be an exit. Yeah.
Did they test it on other vulnerabilities, or just like on general application, or just Heartbleed?
So the question was, did they test it on other vulnerabilities or just like Heartbleed? They highlighted these because they've been major vulnerabilities lately. But the paper was based on the fact that if you know of a vulnerability, so like a buffer overflow vulnerability, you can input that candidate function in as the one that you want to check for, and then it will parse the binary and check against that one. Does that make sense?